So as I was telling, the external potential plugin, it's a very important plugin in CompuCell3D that allows you to impose forces on the cells. We start with the model topics here. In the red box, you can see the things I'm going to present you today. And in green, in the another box, the exercise that is going to be left you to as a homework. So instead of coding all the time, I will ask you to load the exercise I already uploaded to the demo materials day 4, exercise 4.1, and opening in 2 edits. So instead of code, I will go over the codes and explain step by step what is done there to implement the simulation we are building. First, we are going to start with the motivation for this particular lecture. The motivation is the single cell migration. Okay, we have this behavior of a cell that cells are always moving around in general. The big question is, how do the living cells, isolated or collectively, move around within their environment? Okay? Remember, we can put some examples here that we know that there is crawling and migration in many processes in biological development. We can sit here embryonic development, for example, the gastrulation process, the cells from the starting egg move to rearrange to form spinal cords and so on. We have motion in wound healing. When you hurt yourself, there is a scratch or something like that. So cells have to move to that position to close the wound and recover the tissue. We have inflammatory response when your body is answered to some external disease, for example. Cells attack these intruders. We have cancer metastasis when cells detach from the main tumor and invade the other organs of the organism and many other pathologies. So we have to understand and try to simulate how do the cells move. The question is that the movement of the cells can be due to different factors. For example, we have external mechanisms that make the cell move. We have this spermatozoa way to movement, a flagellum movement. We have this paramecium movement, which is cilia around the body of the animal. And also we have another kind of movement that are internal mechanisms. These internal mechanisms can be lamellipodial, like this one you are seeing now. We have the amoeboid movement, like amoeba movement. This is where the name comes from. And also we have the one we are going to focus, which is the lamellipodial movement. We are going to pay more attention to this last one, because this is most particular way model we want to build. So even inside each lamellipodial movement, we can have different behavior of the movement. In this movie, I'm going to try to stop it in steps. The first movement is diffusive. The diffusion, the cell doesn't go anywhere, just play around. The other one, the cell has a preferential movement. The second one here, cannot pause this. Oh, okay. See, this is diffusion. Persistent one, here the cell goes to somewhere. And the other kind of movement is when the cell have part a preferential motion, then stops a little bit, then turns diffusive, and then starts to move in a preferential direction again. All these movements here are produced, let's say, by the front part of the cell. Here is a fibroblast. We can divide the fibroblast with this tail here, that right side, the cell body where the nucleus is, and the lamellipodium, which is compounded by the lamellum and the front of the cell here. In the bottom image, you have a fluorescent image of this intricate actin networks that are constantly rearranging to make the cell to move. And how does that work? See, there is in this front part of the lamellipodium here, we have a high concentration of actin monomers. These monomers starts to attach to one another to build these structures here. And this structure push this front of the cell, exerts a force of the membrane from inside and move the cell forward. We can see in this small movie here how this arrangement of monomers occurs. See? Here is this, I mean, the source of the monomers, and they are attaching to the front and detaching from the end of the fiber, because, you know, there is a fixed number of monomers. So there is a kind of recycling here with, it's like a treadmill, detached from the tail and attached to the front, and the cell goes forward whenever it wants. Okay? So this is the main machinery, the engine that makes the cell move, the lamellipodial movement. Okay? Now, the big feature of the lamellipodial movement that is characteristic of eukaryotic cells are the persistence. Remember the movie you saw before? The cells move around and then decides to go in one direction and goes like this. See, the cell moves, stops, change direction, move, stops, change direction, and so on. So there is between two stops, let's say, there is a persistence time where the cell goes in one single direction. The problem is that we already saw in CompuCell that CompuCell doesn't have persistence time. I think once you create a cell in CompuCell, the cell wanders in the grid, as we saw other day. They move around in a random motion, and doesn't go anywhere. If you average the mean displacement, it's going to be 0. Okay, so we have to impose a persistence random walk in the cells, and this is how we do that is the role of the external potential plugin. I mean, we are going to emulate a way to impose force on the cells. Remember, CompuCell doesn't work with forces. It works with energies and difference of energies. Sure? We cannot put a force on a cell. We can change energies. So we have to go back to physics again and remember that the difference of potential energies produces force. We did that already when we defined the pressure in the lecture 2 days ago. The pressure was the variation of the volume energy with the distance. This is how we implement it here. Force is minus the gradient of the potential energy. So we introduce a new term in the energy of the system that will force the cell to move in a given direction. And this term, the energy term, has this shape, this expression. A delta E is minus F dot delta X, where F is the applied force, XY is the position where the force is applied. This dot here represents the scalar product between two vectors, the force and the delta X, which is the cell displacement. So remember, since we have a vector, we have to open here this scalar product. And opening this scalar product, we are going to work with components of them in each direction of our system. If we are dealing with a 2D system, then we have two components for each vector at most. So expanding this scalar product here, we have this expression here. Suppose that we are dealing with three dimensions here, with this complete form. So going ahead, we can now say that if you apply a force for example, in this green cell here, in this position, the cell will move according with the external potential plugin implemented through this variation of energy. Not that the external plugin acts not on the energy, but in difference of energies. Not the energy before and the energy after. No, it is a term which is added to difference between two instances of the movement. Okay? Okay, we have the sign here to make the cell move in a positive direction. If you use negative energies. So moving on, let's try to understand a little bit before go to exercise about periodic boundary conditions. We have been talking about the periodic boundary condition a lot, but I'm not quite sure if everyone understands that. Just to clarify a little bit, let's see. Our simulations occurs in a finite space, 2D space, for example. Here it's a plane, XY plane, XY. So it's a finite space. So it costs too much for the computational time and memory to increase this grid too much. So we trick this by using periodic boundary condition. What does that mean? You saw already. When the cell moves in a plane and it crosses the border, it appears in the other side, in the opposite side of the grid. Pedro talked about yesterday about the arcade games. No? So object disappears at the right side and appears in the left side. Disappears in the upper side and appears in the bottom side. So we can understand that if we twist this sheet, the XY plane, this way. Look here. This is a very interesting and clarifying example. This is the plane. Now we are turning the X boundary periodic and the Y boundary periodic. So the corners, all the four corners of the plane come together at this point here. And then we have like a torus, or it's a torus, like a donut or a tire, a car tire. So instead we have a limited space here, we have a unlimited space because the cell or the object which is moving over the torus doesn't encounter an end and keep you walking always. Okay, I hope this clarifies your concept about the periodic boundary conditions. Just because we are going to deal with periodic boundary condition a lot in this next example. Let's analyze the example exercise 4111. Then you can open it in to edit. Here is the roadmap for the exercise as usual, but I'm going to step by step and not coding, but look at the code you already have. As usual, you create everything in the simulation. If you want to create simulations, you are free to do that. The usual steps for the initial simulation. Behaviors, cell type behaviors. And now we are going to, after your wizard is finished, let's go to XML5 and change the box min and box max region to 120 to 129 for both X and Y dimensions. This means a small region of 10 pixels by 10, a square of 10 pixel size. And the width of the cell is 10. And you put there a single cell that I call the move cells. Okay. Advancing, you have now to include, because it's not, this doesn't come with the wizard, in the steppable, in the start function, we change the target volume for the cell as 300, the lambda volume to 10, and we add the components of the vector force, X and Y, to 20. What you should see? You should see something like that. Okay, see, this is, look, the cell is moving in a diagonal, interdiagonal of the grid in a constant movement. The movement is constant because we have chosen that the components of the lambda vector are constants. So the cells move always the same way, always in the same direction because the force is constant in that direction. Since both components of the force are equals, the movement is in the diagonal of the grid. And again, we are using the periodic boundary conditions. The cells reach the upper corner, right corner, and appears in the left lower corner without any harm to the cell. Okay? So let's change a little bit the code. Sorry, I forgot to mention, we did that to achieve persistence. So now instead the cell wandering around the lattice, we have a directional movement promoted by the external potential plugin, by the force. Okay? Let's make the force, the cell to accelerate. To do that, we have to modify the code. So now you have to load the next example, which is the 4112, and load it in the to edit. And let's see the modifications. Okay, it's the same code as before, but if you are coding, you implement these modifications by typing. But to save time, let's get it ready. So the first thing is to do, well, acceleration depends on time. So we have to define a time interval to change the motion or to change the force. So we define it very, very beginning of the steppable, a global variable here that I called time interval, and I put it equals to 100. And I change now the lambda vex and vex x and lambda vex y definition by a function of MCS. See, now instead of the constant value of 20, I have this value of MCS divided by time interval. So at each time that there is a change, the value of the lambda vex changed. Probably you see this. The cell starts slowly, but it accelerates with time. This is why both lambda vex are changed. Since both are changing equally, the cell continues to move over the diagonal of the grid. Both components are equals. Okay? Okay, let's move on. Another thing. The question, can the cell accelerate forever? Let's see. Because the way the code is written, it's always increasing the lambda vex. So it would expect that the cells reach infinity speed. Let's see if that's possible. To do that, let's go to the other exercise, 113. Open it, and let's look at that. Now we have to keep track of the speed of the cell to see if it is accelerating forever. To do that, more physics, we have to calculate the components of the speed in each direction and calculate the intensity of the speed with this expression, the modulus of the vector velocity vector. The intensity of the lambda vector is also calculated as usual, the sum of the square of the components of the vector, the square root of them. So we have in this page here how to calculate the speed and the intensity of the force. what we are going to do now is to plot speed against force. This is what you have in 4113. To do that, you can follow the exercise, the code. We have to create a dictionary here, which saves the old position of the center of mass of the cell. Why? Because remember, according with the previous expression, the speed is the position at a t plus delta t minus a t before. So we needed two consecutive positions of the center of mass of the cell. This is why I am creating this dictionary to save the old position of the center of mass. And as usual, we add the plot window to see the plot of the speed against lambda vec, against the force. And we have now to be careful with the boundary conditions, the periodic boundary conditions. Why? Because when the cells cross borders, we have to correct the right position for the center of mass. You know, dx, for example, if the cell is at the position 255, it's in the border, the left border, the right border of the x axis. And the next step, the cells cross the border and appears in the x equals to 1. How much the cell has moved? If I don't take care, if you look at this line 36, the position would be 2 minus 255. I mean, the displacement would be minus 253 pixels, which is wrong because the cells only moved 3 steps, 3 pixels from 255, 0, 1, 2, and appears in the left side. So we have to correct this delta x, making this simple operation is corrected by the length of the grid. Okay, then you can have a look more carefully in this expression to convince yourselves that this must be done. Once you have corrected dx and dy, we can calculate the speed according with the previous formulas. The square root of components square, and I will divide by the time interval that I'm measuring both positions. Speed is displaced over time, okay? And the lambda vector, the intensity of the lambda vector is the same. It's square root of the squared components. Then I am able to plot this. You have everything done, you can plot it, run the code. What do you think that happened? See, if you let the simulation run for 1-2 minutes, you can see that the cells reach a maximum speed. I mean, it accelerates during certain amount of time. Here, the speed is growing, is increasing with lambda, but after certain amount, after value of lambda, the cell doesn't accelerate anymore. Why? Remember, the code is always increasing lambda vex, always, with Monte Carlo step. The reason is because we have competition between plugins. again, to indefinitely to increase speed, the cell should be able to stretch the most because the force is increasing a lot. But competition with contact energies and volume energies doesn't allow to do that. So the cells reach a maximum speed. It's a probability of acceptance stuff. This is why it doesn't grow forever, the speed. Okay, continues. Now, let's change the trajectory. Let's make the cell move randomly, not in a straight line. To do that, we have to change the components of the vector force, the lambda vex. Again, so now you go to exercise 4114, and let's look at the code. You have a code there that is the same as before. You have this graph window now a little bit different because now we don't want to see the speed against force. We want to see the position, the trajectory of the cell. I mean, how the cell is moving over the space onto the plane XY. Yeah? So we are going to keep track of the position of the center of mass, X and Y. To make the movement random, we, in the first line before the time interval definition, see that I have changed a little bit the time interval value from 100 to 1,000 here. And we also imported the random library from Python, the uniform random number generator. Okay, and this is how we are going to change the values of the lambda vector. Look at this bottom panel here, lines 31, 32, the way I'm randomizing the lambda vex. There is a modulus, 120 for both, and this modulus is multiplied by a random number, a uniform number between point minus 27 and plus 27, 0.27, both. So the random number generator picks a number between minus 20.27 and plus 20.27, multiplied by 120, and this is the new value for lambda vex. Put it to run without anything else, just the way it is. We should have gotten something like that. The motion starts with a zigzag trajectory, and when the cell crosses the border, there is such spikes in the plot here, which occurs because we are not correcting again for the position in the grid. Now is that point. We are moving from a point near to 0 to a point near to 500, for example. And the displacement, if you don't correct, would be 400 something. But it is not. It's only for 3 or 4 pixels. You have to correct that. Okay? Those corrections are in green in the code. Commented lines here. See? You have the steppable now. Please uncomment the green lines to include in the code. In the start function, you uncomment line 16 to 19. And in the step of the steppable, you uncomment lines 32 to 45 and comment line 46. This small routine here in green in the steppable is the correction for the position of the trajectory. We don't have much time to go over it, but it's similar to the previous one. We have to put the cell in the right position, and since now we are dealing with trajectory, we have to add that amount that was moved in that interval to the total displacement of the cell to have the trajectory. This is done in line 39 and 40 here. X position and Y position is the previous one plus what have changed in this particular interval of time. Okay, when you do that, now you can run again the code. You have this. No more spikes, and the plot is increasing accordingly with the trajectory of the cell, no matter how many times the cell crosses the boundaries of the lattice. So again, you have this in 4.1.1.4. The last thing I'm going to introduce today is this. Let's build a more realistic cell. Because so far our cell is a bunch of pixels with no structure. But the real cells is much more complicated. We saw that before. For example, we can make a simple model of the cell as compounded by 4 or 5 components. The nucleus, the cortex, that is the membrane, the cytoplasm, and the lamellipodium. And if you an external participant in the model, the substratum where the cell is attached to, and the medium field. Okay, this is the motion. Again, let's see the motion here just to see it. Inside the cells are the structure of the cells, the nucleus, the mitochondria, and the lamellipodium is quite thin, is barely seen, the lamellipodium here, for example. See? The lamellipodium is very thin, and the body of the cell is much thicker because of the nucleus. The nucleus is very, very high. So the basic model, one of the basic models we have, is the one proposed by Abercrombie for the cell crawling. How that happens? See, there is the cell. The cells stretch its tip to a certain, the polymerization of the actin network here produces the tip towards the tip attached to the substrate, releases the end of the cell, and the fiber networks that is inside the cell pull the cells in that direction, contract the cells, and the cells move to the right. And things start over. So it's like a treadmill, actually. Go there, pull back, go there, pull back, go there, and so on. Okay? So we want to build now a kind of more realistic cell that have at least three components: the lamellipodium, the cytoplasm, and the nucleus. It's a three-component cell, okay? As the one from Abercrombie. We are going to use this external potential local flex plugin to move the cell in a random direction if you want. And we are going to watch the trajectory in a exercise that is a homework. This exercise is the 4121. Please open it. So this is, as I said, a trick simulation because we have to build our three component cells. What do we do that? We have to create three different types of cells: a nucleus, a cyto, and a lamella, and make they work together as a single cell. Okay? So the first thing that you're gonna see in the XML, in this uniform initializer, is how after, of course, you have to create the simulation with three kinds of cells: cyto, lamel, and nucleus. In the wizard, you have this in the code already, but how to arrange them at the beginning. This is what I'm showing here in the uniform initialize. I have three cells here: cyto, lamel, and nucleus. And they are all together, one aside of the other. If you step the code now, not put it to run, only start with one step in the player. In the steppable, we have to define how big each cell is, each part of the cell is. Usually the cytoplasm, the part of the kid, it has a cytoplasm. The cell is the bigger one. Let's make it as a reference for the other parts of the cell. So I'm defining here cytovol as 300 pixels. And then I'm giving values for the target volumes of each kind of cell. So the target volume of the cyto is cytovol. The target volume for the lamel is 30% of the volume of the cytoplasm. And the volume of the nucleus, the target volume of the nucleus, is 20% of the volume of the cyto. So I have 360 and 90 pixels for the other components. They have different target values. Now you can run it. Give you one step. So you have this image on your graphics window. We have at the beginning, because I just give it one step of Monte Carlo, so they not reach the target's volume yet, so they are always equal squares. If you put it to run, they quickly achieve this configuration. We're saying the cell is wrong, because remember, we want that the nucleus goes inside to the cytoplasm. What we're going to change to fix that? The change is in the contact energies. Remember, I don't remember who did, I think it was Hayden who talks about a hierarchy in the cell sorting, adjusting energies between among all the cells in the simulation, in the sorting simulation. This is what we have to do now. So if you now go to the player and in the left panel, in the player model editor, you click in the contact plugin, you can open all the energies, the contact energies between two pairs of components, medium, cyto, medium lamel, lamel, so on. And is a very, you have to be very patient to adjust everything. Okay. So I did that already. And I got a good set of parameters, which are those. This is in the, I think it is in 4.1.2.1 exercise. Everything is fixed already. And if you put the simulation to run with these new values here, we have the correct value here, correct shape for the cell. See, the nucleus is the yellow part, the purple is the cytoplasm, and the green is lamellipodium. See? The nucleus inside, lamellipodium around the cell, like should be. Now we are going to use the external plugin to make it move. Again, we import, this is in exercise 4.1.2. You go to line 3, you have the import the uniform generator number again, because you want a external random movement. You include the lambda vex as before with a uniform number generated to change the values of the vex, the components, and you run this new simulation, the 4.1.2. You have this. Now we have a much more between commas realistic cells. Nucleus around circumvented by cytoplasm, being pulled by lamellipodium. And see, it's really being pulled by lamellipodium, because here in line 26 to 35, where I implemented the external potential plugin, I'm only implemented force on the lamel, not in the other parts of the cell. Okay, so the green part is the real engine of the cell, because the lambda vec for the cytoplasm and the nucleus are 0. They are moving because the green is pulling them forward. And in a random motion, as it's like that first one of the first move, a persistent motion with some random walk. I mean, in average, this, if you take a long time of observation, we have a random motion here. The cell doesn't go anywhere because he walks in one direction during a certain amount of time, then turn direction, go there, then change that, come back. And if you average that after a long time, the total displacement should be 0. But small time intervals, it has a preferential movement. Okay? So I will stop here. I have covered a lot of things. Thank you for your attention. But please, if you download the presentation, in the presentation we have more exercise, including one where I create a three-dimensional cell with three components like this last one, which moves in a flat surface. It's a 3D, really 3D cell. And after that, there is another exercise, very cool, where I make a bunch of cells move in a flowing, bunch of cells flowing inside a tube with a constraint and an obstacle in the middle. Please have a look at that. You're going to be happy with that. And the exercise, the codes are in the demo materials as well. Okay, thank you.